What if I told you that there are real monsters out there in the universe? Not like in the movies, but monsters made of pure physics. I'm talking about objects so unbelievably massive, so dense, that they literally eat light and twist the fabric of reality itself. Today in this explainer, we're going right to the edge of what we know. We're diving headfirst into the incredible enigma of the black hole. So let's start with this simple question. What if gravity, the force that keeps us on the ground, could get so incredibly strong that nothing, and I mean nothing, not the fastest ship you can imagine, not even light itself, could break free from its grip? Well, if that happened, you'd get something that just seems impossible, right? A patch of perfect cosmic darkness. You'd get a black hole. Okay, so first things first, let's get rid of the idea of a literal hole. A black hole is actually the exact opposite. It's an insane amount of stuff, of matter, that's been crushed down into a space smaller than a single atom. All that mass in one tiny point creates a dip in space-time, a gravitational well so deep that it basically becomes a prison for light. It's the one place in the universe where our rulebook for physics it falls apart.
So what is it that makes this trap so final? It really all boils down to one critical, invisible line, a boundary that marks the point of no return.
Now, this isn't some physical wall that you could, knock on. Think of it more like the edge of a massive waterfall in space. Before you get to the edge, you could still fire up your engines and get away. But the second you drift over that line, the event horizon, that's it. You're caught in the current. There's no turning back. Every single path from that moment on leads to only one place. The very center. All right, so an object this extreme has to have an equally extreme origin story, right? You don't just, find a black hole lying around. It has to be forged in one of the most violent events the universe can possibly cook up, the explosive death of a truly gigantic star. For millions, even billions of years, there's this epic battle raging inside every huge star. On one side, you have nuclear fusion, blasting energy outwards. On the other, the star's own incredible gravity trying to crush it. But eventually that fuel runs out. The outward push just stops. And in that instant, gravity wins. It lands the final devastating blow. The star's core collapses, which triggers a supernova explosion so bright it can outshine an entire galaxy. But while the outer layers are blasting away, the core just keeps crushing inward, smaller and smaller, until it's squeezed into a point of infinite density. And right there, a singularity is formed. A new black hole is born. And that whole process, that gives us what we call a stellar mass black hole. You get a few suns worth of material crushed down into something the size of a city. But then there are the other ones, the true titans of the cosmos, supermassive black holes. These absolute monsters are hiding at the center of almost every galaxy, including our own Milky Way. And they don't just weigh a few suns. They weigh millions, sometimes billions of suns. How in the world did they get that big? Honestly, that's still one of the biggest puzzles in all of cosmology. So this brings up a pretty obvious question, right? If black holes are black and space is also black, how on earth do we even find them? Well, the trick is you don't actually look for the hole itself. You look for the glowing, chaotic mess it makes right before everything disappears forever. So let's clear up one of the biggest myths right now. Black holes are not cosmic vacuum cleaners. They don't just wander around the universe, sucking everything up. Things have to get really, really close to be in any danger. And when they do get close, it's not so much a suck as it is this violent, beautiful, and, ultimately fatal dance with gravity. And the evidence of that dance, its signature move, is the accretion disk. See, as stars and gas clouds get pulled in, they don't just fall straight down. They get whipped around into this flat, spinning pancake of superheated matter. The friction and gravitational forces in this disk are so extreme, it heats up to millions of degrees, causing it to glow brighter than all the billions of stars in its galaxy combined. That blinding light? That's our smoking gun. It's what points us to the darkness hiding at its center. This is why they're not just cosmic drains. They're more like galactic engines. While some stuff is falling in, other material gets supercharged and blasted out from the poles in these enormous jets that travel at nearly the speed of light. I mean, these jets can stretch for millions of light years across space, and they're so powerful they can actually control whether or not new stars can form in their galaxy. So they're not just destroyers, they're cosmic architects too. But the real mind-bending part of the story isn't just what happens around a black hole. It's what happens when you get too close. This is where we have to throw out our everyday understanding of physics because things get really, really weird. Okay, first up, there's a process with a name that genuinely sounds like it came from a sci-fi comedy. Spaghettification. And yeah, it is exactly what it sounds like. If you were to fall feet first into a regular-sized black hole, the gravity pulling on your feet would be so much stronger than the gravity pulling on your head that it would literally stretch you out, like a piece of spaghetti. You'd be pulled into a long, thin stream of atoms. A pretty gruesome way to go, but you have to admit it's an unforgettably strange idea. And it's not just space that gets all warped and twisted, it's time, too. Einstein's theories told us that really strong gravity can actually slow down time. And near a black hole, that effect goes into overdrive. Seriously, if you could orbit a black hole for just 1 hour and then fly back to Earth, you might come back to find that decades, maybe even centuries, have passed for everyone else. A trip to a black hole is literally a one-way ticket to the future. For decades, we all thought that no escape rule was absolute, ironclad. But then, the brilliant Stephen Hawking came along and found this incredible loophole. Thanks to the seriously weird rules of quantum mechanics that happen right at the event horizon, it turns out black holes aren't perfectly black. They leak. They give off this tiny, tiny trickle of energy, which we now call Hawking radiation. And what that means is they're not eternal. Over unbelievable, mind-bogglingly long timescales, they can actually evaporate and just disappear. And that last part, the fact that black holes can eventually fade away, leaves us with what might be the single biggest puzzle in all of physics. See, there's a fundamental rule in our universe that says information can never be truly destroyed. The unique blueprint for a star or a planet or even a person, it can't just vanish. So what happens when you throw a star with all of its one-of-a-kind information into a black hole, and then the black hole itself evaporates? Where does all that information go? This is called the information paradox, and it's one of the deepest mysteries we've ever faced. It's a perfect reminder that even at the heart of complete darkness, there are still questions we don't even know how to ask yet.